Hello, I'm Katherine Lucas, and this is Developing and Validating a Standard Operating Procedure for Quantitative Analysis using Central Washington University's X-Ray Diffractometer. Woo! So this slide is showing an overview of the presentation, including an introduction and background, which is basically your tools for understanding this project, what the data means, etc., etc. Then methods, which is what I did and how I did it, and then results, which is what the data looks like and how do the different methods compare, etc. And then discussion and recommendations, which is what do the results mean and what do I recommend going forward for future projects. And then, well, future work. So what's the next step? So X-ray diffraction is versatile and widely applied. We're talking pharmaceuticals, geology, cement analysis, you name it. And operating procedures exist to standardize the methods for different instruments, materials, etc. for different labs, but they need to be evaluated and refined over time. And this study is meant to lay the groundwork for procedure refinement. You know, I said developing, but it's more like refining an existing procedure. So, how does X-ray diffraction actually work? Well, I'm going to use this figure to help explain it. So this figure shows a hypothetical example using a grain with 3 different sets of atomic planes here. And depending on the orientation of the grain, different plane sets diffract the X-rays that hit the grain, and the X-rays are shown by the black line, the black arrows here. So, you know, you could have plane set 1, plane set 2, plane set 3, or none of the planes get detected. So the main takeaway from this is that X-rays are diffracted by the atoms in a material depending on the orientation of said material, and that, as we'll see, diffraction causes peaks in X-ray intensity at different positions. So the rest of this figure shows how different grain sizes affect measurement. So for a hypothetical well-ground sample, the grains are small enough that there's lots of grains and lots of orientations being hit by the X-ray beam, so they all get a chance to diffract the X-rays, so they're all detected clearly by the instrument as a result. So if we were to look at the hypothetical data collected from this, all the peaks in intensity would appear in the data as they normally would. But for a hypothetical underground sample, shown here at the bottom, the grains are too big for all the orientations and atomic planes to be hit by the X-ray beam. So in this case, they wouldn't all be able to diffract the X-rays, so they wouldn't all be detected by the instrument. And if we looked at the data from this hypothetical example, the peaks in intensity would not appear as they normally would, so the data would look really weird. And this is the main reason why samples are ground down to a very fine size before we do XRD measurement. And I've been talking about these peaks in intensity in the last couple slides, so let me explain a little bit more about what I mean. So these 2 graphs show XRD measurement data for 2 different samples, olivine and silica flour. And the x-axis is the position of the X-ray detector in the machine during measurement, and then the y-axis is the number of X-rays that hit the detector in a given position. So this is intensity in counts. And these patterns, as you can see here, are unique to different minerals. And these peaks are basically caused by the grains in the sample diffracting the X-rays during measurement. So now to get into methods, so there'll be 3 main points here to discuss. The sample grinding, including the conditions and the grain size analysis that I did, and then XRD measurement conditions, specifically talking about sample holder type and measurement duration, and then purity assessments where I'll discuss some of the analysis process. So, right into it with sample grinding. So I mechanically ground all the samples using a ball mill. A simplified sketch of a container in the ball mill is shown here on the right. You put steel balls in it and your sample, and then the instrument shakes the container back and forth rapidly to grind up the sample. And then after that, you can see the sample looks very ground up and all powdery. So then I took all of those ball mill ground samples, and then I did 2 minutes of hand grinding with a mortar and pestle. And then I took each set of samples and ran them through a particle size analyzer to determine the grain size distribution before and after the addition of hand grinding. So then, getting into holder type, we've got a solid aluminum holder and a 0 background holder. And I won't get into detail on that in the interest of time. But the holder used is important because samples are tilted and spun during measurement. And then for measurement duration, we have 3 different durations ranging from just 8 minutes to 54 minutes for one sample. And then getting into purity assessments now, I compared my data to match units. And match units are previously collected data that serves to be sort of a standard that you compare your data to. And this figure here on the right shows an example of that comparison, with the red line being the data that I collected for an olivine sample, and then the green bars are match unit data. And you use this for mineral IDs, so basically to determine what's actually in the sample. And then once you've figured out everything that's in the sample, you do the software can do quantitative analysis to determine the mineral abundance. So basically how much of each mineral is actually in there. And now getting on to results. So we've got grain size analysis, so basically the grain size distribution for the 2 methods, XRD measurement duration, so 8 minutes versus 54 minutes, and then pie chart results for all the purity assessments. So a quick note before we get into the meat of this, ball mill grinding duration does vary among different minerals, but the hand grinding is the same amount. So the blue solid line here is for just ball mill grinding, the grain size distribution, and then the orange dashed curves are for ball mill and hand grinding. The x-axis is the size in microns of the grains and is logarithmic. The y-axis is basically the amount of sample by volume that is that particular size, and it is in percent. So as you can see, there are 2 key differences after adding hand grinding: the decrease in the amount of larger grains and the increase in the amount of smaller grains. And you can see sort of this systematic shift in the curve to the right with the addition of hand grinding for both of these samples. And then getting into measurement duration, the 54 minutes produces much more distinct peaks than 8 minutes, which you can see here. And there are 2 main things to look at. First is that the 54-minute data has higher peaks, which mean they have more counts. And this is important for qualitative analysis going forward. And the other thing is that the smaller peaks are much more distinct, and this is very noticeable with very small peaks like between 35 and 40 degrees 2 theta here. And then getting into purity assessments, blue is the main mineral, so the percentage of the sample that is the main mineral, and then orange is the percentage of the sample that is anything other than the main mineral, and I just lumped them together for clarity. These samples here on the top row are the ones that I selected for future work because they're all relatively pure and represent a range of mineral types. But as you can see, the purity is a little bit variable across the board. And then getting into discussion and recommendations. So, as shown previously, there are systematic differences in the grain size after adding hand grinding to ball mill ground samples, but I believe that these differences are helpful because they're effective at reducing, further reducing large grains left after ball mill grinding, which, as shown previously, have an adverse effect on measurement. So this image on the left is the ball mill. I used this particular container that I'm circling for sample grinding. And then this image on the right is the particle size analyzer that I used. So getting into XRD holder type and measurement duration. Now, I didn't show the data, but the zero background holder does present a lower risk of spilling, which is important because spilling can ruin the data and contaminate other samples during measurement. But it can also be used to measure a lower amount of sample, which is good if you don't have a lot of sample to use. So I definitely recommend it for those reasons. And then I definitely recommend collecting data for at least 54 minutes. It definitely produces superior data compared to 8 minutes. And then future work, so what's next? With sample grinding, there's many options to explore, including addressing large grains and overgrinding problems and evaluating other grinding methods as well. And then with synthetic rock mixtures, those are really the next step with XRD measurement and analysis methods evaluation, but that comes with the necessity of doing purity assessments with better quality data and match units. And but once we can do that, then we can use those rock mixtures to evaluate different measurement conditions and quantitative analysis procedures for multi-phase samples, like rocks. And those synthetic rock mixtures should also be used to evaluate the precision and accuracy of quantitative analysis results as well. And that is all I have for you today, and thank you very much for listening and watching.